Hey everybody, and welcome to How-To Videos with Dr. Amy Gates. This video is part of the massively open online video textbook for Introduction to Statistics. To find other chapters and other information, check out mathandstatistics.com. This particular video is going to focus on using the zTable, calculating z-scores, finding normal probabilities and percentages above, below, and between values, and so on. So as a reminder, when you have data that is normally distributed, it has certain attributes. Not all data is normally distributed, but some data, such as female height or male weight or things like this, are normally distributed. And what that means is that if you were to collect a very large quantity of that data and graph it as a histogram, that histogram would be bell-shaped. The mean, median, and mode of the data are very similar in value and are in the center of the data set. The histogram would be symmetrical and would have one mode. And it would also follow the empirical rule, which I'll skip ahead to show you what that looks like. I have a separate video that deals with the empirical rule, but we'll come back and forth to that in this video as well. But when you have data that's normally distributed, one of the great things about that is that you can estimate where certain percentages of your data are. And the empirical rule helps you to do that. This rule is also called the 68, 95, 99.7 rule. And what it tells you is that given any data set mean, and if you also know your standard deviation, and if you don't, you can always calculate both, about 34.1% of the data is between the mean and -1 standard deviations from the mean. Another 34.1% is between the mean and +1 standard deviation, and so that gives you a little over 68% of the data between -1 and +1 deviations from your center. And that's where the 68 comes from. And that's actually most of your data. And so if you think about something like female adult height, for example, most adult females are actually of a similar height. Some are a little taller, some are a little shorter, but the vast majority of females are close in height. And so that's why female height ends up being normally distributed. The 95 from the empirical rule tells us that, in fact, 95% of any data set that is normally distributed will have its values between -2 and +2 standard deviations from the mean. And so just as a review of normally distributed data, if you know that your data is from a normal population, or if you collect a very large data set and you build a histogram, and your histogram has a normal shape, then there are several things that you can do with that data. One of them is using the empirical rule, but the other is using what's called the zTable. Now this is an image of the zTable, and what the zTable allows you to do is it allows you to convert or standardize any value in your data set, assuming that your data is normally distributed, to an equivalent z-value. The z-value is, in fact, the number of standard deviations your value is from the mean of your data set. And we're going to take several examples so you can see how that works. But once you have the z-value, you can come to the zTable, look up that value, and then all of these numbers inside of the zTable give you exactly the percentage or probability of values below that point. And this will make a lot more sense when we actually look at examples. So let's just do that. In the first example, we're going to ask the question, suppose we have a data set of female height and we know that it's normally distributed, which is always required if you want to use the zTable. We also need to know the mean of our data set and the standard deviation, or the deviation of our data set. In this particular example, the mean of our data set is 65 inches. That's about 5 feet 5 inches. And the deviation of our data set is 2 inches. So we can come and fill these values in to their equivalent locations on this estimate of a bell curve. The mean is always right in the center when z is 0. And then because the deviation of our data set is 2, if I add 2 to this value, I get 67. And that's exactly one standardized deviation from the mean. Each deviation is a value of 2 inches. So when I add another 2 inches, I'm at my second deviation from the mean. Remember, when you say that your data set has a standard deviation of, say, 2 inches in this case, that means that each step away from the mean, or each standardized deviation away from the mean, is made up of 2 inches. So our center is 65 inches, 1 step away is 67 inches, 2 steps away is 69 inches. If I go shorter or backwards, 1 step away is 63 inches, and another step away is 61 inches. So each step, or each deviation, or each z-value is 2 inches, and that was defined in our problem. If you don't know the standard deviation of your data set, you need only calculate it. Now, given any value in your data set, once you know the mean and once you know the standard deviation, given any value, we'll call that value x, you can take that value and you can do what's called standardizing it. You can convert that x value into its equivalent z value. And we can visually do that here, and there's also a formula that's essentially doing the same exact thing. So let's see how that works. Let's say I want to use the value 67. So let's say I'm wondering, what is the z value, the equivalent z value, for a height of 67 in my particular data set where the mean height is 65 and the deviations are 2 inches? Well, okay, if I know the mean is 65 and I know that each deviation is worth 2 inches, I know that 67 is 2 inches above 65, so it's 1 standard deviation above 65. The z-value is exactly the number of standardized deviations you are from the mean. The z-value is positive when you're above the mean or to the right of the mean. The z-values become negative when you're below or to the left of the mean or less than the mean. So visually, we can see that a height of 67 inches is exactly 1 standard deviation above the mean. Each deviation is 2 inches. We can also use the zScore formula to make that same exact calculation. The zScore formula is always the value you're trying to convert to the z-value minus the mean divided by the deviation of your data set. Well, we're trying to convert 67 to its equivalent z-value. So we subtract the mean of our data set, which is 65. We divide by the deviation of our data set, which is 2. 67 minus 5 is 2. 2 divided by 2 is 1. And so, of course, we get 1, which is exactly what we can see that it is here. So when you calculate a z-value, what you're actually doing is calculating the exact number of standardized deviations that your value is from the mean of your data set. So why do we do this? Why do we have to calculate z-values? Why do we have to standardize our data? Well, here's the answer. There's only one zTable. It's a standard zTable. In this zTable, the value of 0 represents the mean. It's the center. And you can see here that at the value of 0, you get a 0.5 in the table. That means 50% of the data is below 0 and 50% is then above 0. So if there's only one zTable, but it can be used for any normally distributed data set in the universe, there has to be a way to convert the values of your given data set so that you can use them in this table. And that's actually what you do when you calculate a zScore, is you standardize the value in your data set so that it can be used in the zTable. Let's take another example. These are some visual examples without using the formula so you can get used to what it looks like when you convert a data value of x to its equivalent z-value. 65 is again the mean of our data set with a deviation of 2 inches. And so I filled that in here. The mean is 65. That's z is 0. 1 standard deviation away from the mean is 67 inches. 2 standard deviations away from the mean is 69 inches, and so on. So the data value, or the x value of 65, is the same as a z-score of 0. The data value of 63 is the same as a z-score of -1. The data value of 61 is the same as a z-score of -2. The data value of 67 is the same as a z-score of +1. The data value of 68, which would be squeezed right in between here, is a z-score of 1.5. It's between 1 and 2. Now you might ask, what are these little s's here? What do they stand for? That's the standard deviation of my data set. So this is one of my deviations. My deviations are all worth 2 inches. So this is 1 times 2, and that's where I get 65 plus 2 is 67. Each of my standard deviations from my data set are worth 2. So each data set has its own mean, which would go in the center, and its own deviation. This deviation tells you how much each of these steps is worth, and that's what that S there represents. In this case, each of my steps is worth 2. So it goes up 2, and it goes up 2, and then if I start here, it goes down 2, and then down 2. Now, these are easier to visualize because they're even values. But you can also use the Z formula, and I'm going to skip ahead here for a second, to actually calculate the number of standard deviations, even when it's not a perfectly rounded value. So let's take a look at this example for a moment. This example uses a different data set. This data set is for final exam scores. To create this data set, 1,000 final exam scores were collected. The mean was calculated at 75. And the standard deviation for this data set is 5.5. That's why on this bell curve, because they are normally distributed, the mean is 75, that's our x value. The equivalent z value is 0, because that's the center. Each step is 5.5%. So to go to the first step, I had to add 5.5 to this, and that gave me 80.5. So 80.5 is the same thing as a z-value of +1. It's one standard deviation, one deviation above the mean. 2 deviations, which is 11 points, is an 86. If I add 11 to 75, I get 86. So that's 2 steps, or 2 deviations above the mean. And remember, each deviation is calculated by knowing the standard deviation of my own data set, which is 5.5. Same thing going the other way. If I subtract 5.5 from 75, I get 69.5. So that's 1 deviation below the average. If I subtract 11, which is 2 deviations, I get 64. So what can I do with this kind of information? And again, what I'm hoping that you see here so far is that as long as you know that your data is normally distributed, and as long as you know the mean of your data and the standard deviation of your data, you can fill out the bell curve accordingly so that you know all the equivalent z values. You can also guesstimate z values. Like this z value is 1.5 because it's between 1 and 2. So the score between 80.5 and 86 would be equivalent to that z value. These are all equivalent values. Any data set can be converted or standardized into its equivalent z values so that you can then use the zTable to answer questions like, what's the probability of a student getting a 75%? Or what's the probability of a student getting between 67 and 82%, and so on. So here are 3 types of questions that you can answer using the zTable and having a data set that is normally distributed with a mean value that is known and a deviation that is known. So we're again going to use our final exam score data set with a mean of 75 and a deviation of 5.5. We're going to do these 3 examples. The first one is we're going to use the zTable to calculate the probability that a student will score below an 81%. This is also the same question as what are the percentage of students that scored below 81? Kind of means the same thing. This is also, I've noticed, phrased as what's the area under the curve below 81. The area under the curve below 81. So there's a lot of different ways to phrase this. Sometimes you'll look at this as 100% of the curve. Or in area terms, the entire curve is 1 and these are all fractions of 1 and so on. Some people might look at this as percentages, which we have a good graph over here. This is about 34% of the data. Here's another 34% of the data. Together, this is about 68% of your data in your data set. If I were to start here and only want the data on this side, that's about 15.9% of the data. The data from here all the way this direction, meaning anything under a 67 in this example, is 84.1% of the data. So area under the curve or percentage of the data or probability of landing in this area all essentially mean the same thing. And they're all calculated the same way using the zTable. So let's do number 1 first. Number 1 says use the zTable to calculate the probability that a student will score below an 81. Step 1 in using the zTable is always the same. You must convert the x value from your data set to its equivalent z value. You use the formula to do that by taking your x value, 81 in this case, subtracting the mean of your data set, which is 75, dividing by the deviation of your data set, which is 5.5. When I do that, I get 1.09. That tells me that the equivalent value to 81 is a z-value of 1.09. Let's make sure that actually makes sense. Let's go back and see where is 81 on this bell curve of final exam scores. Well, 81 is just above here, right? Here's 80.5. 81 would be somewhere right around here. This is 1 standard deviation from the mean, or z equals 1. So 81 would be just above z equals 1. And that's exactly what it is. It's just above z equals 1. It's 1.09. Once you know the z value, you can look it up on the zTable to get the exact percentage of data that is below that value. The zTable always gives you the percentage of data below the value you're looking up. So again, what happened here? We said, what's the probability that a student gets a score below 81? That's the same thing as asking, what's the probability that the z-value is less than the equivalent z-value to 81, which is 1.09. And if I look up 1.09 on the zTable, so I find 1.0, this is 1.01, 1.02, 1.03, 1.04, all the way to 1.09, I discover that it's 0.8621. In other words, about 86.21% of the scores will be below 81. So the probability that a student scores below an 81 is about 86.21%. That is also the area under the curve below 81. It means the same thing. All right, let's do the next example. In the next example, we want to use the zTable to calculate the probability that a student will score above a 70. Same data set, the mean's still 75, the deviation's still 5.5. But in this case, we want the probability not of below, but of above 70. Let's see what that looks like on our bell curve. 70 is somewhere right around here. It's below the mean, and the probability of getting a 70 or above is actually pretty good because it's all the data that goes from here all the way over. So it's all this data. That's going to be a fair amount. How do we do this? Same as always, first step is to convert the x value that we're considering into its equivalent z value. To do that, we will take the x value, subtract the mean of our data set, and divide by the deviation of our data set. 70 minus 75 divided by 5.5. The result is negative. It is very, very important when you do the subtraction to make sure that if you get a negative result, you keep it. Because remember, when you're to the left of the mean, which we are here, these are negative z-values. And that's important when you look it up on the table. If you use a positive value instead, you're going to be missing out on all this data. So when you do this calculation, your result is minus 0.91. This kind of makes sense because we're looking for the z-value of 70. We know the z-value of 69.5 is minus 1. 70 is just above it, right? So it's going to be a little bit bigger. This value is actually larger than minus 1. Remember your negative rules. And so the z-value for 70 is minus 0.91. Now that you know the z-value, your next step is to use the zTable. Now keep in mind this problem is asking you for the probability above, not below. The zTable always gives you the probability of below. So to get the above probability, you'll have to take the probability from the zTable and subtract it from 1 to get the other side. In other words, the zTable is going to actually give you this probability on this side. You want the other side. That's why you subtract it from 1. Or you can subtract the percentage from 100%. And we'll see both options. So again, we're going to use the zTable first to find the probability of z being less than negative 0.91. Then we're going to subtract that from 1 because we want the probability above, not below. So here's our zTable. Here's our negative 0.91. That's this value here. So the probability of the student getting a score below below 70 is 0.1814. That's what's over, sorry about that, that's what's over here. But we want above. To get above, we subtract that value from 1, and we discover that there's an 81.86% chance that a student will score above a 70. Little over 81%. Let's see if that makes sense. We know that from the empirical rule that we have nearly 68% of the data here, another 13 and change here, and another 2% here. So that actually looks right. From here onward is a significant percentage of the data. And in fact, it's about 81.86% of the data. In the last example, we're going to look at a between question. Same data set, the mean is still 75. The deviation is still 5.5. But the question's saying use the zTable to calculate the probability that a student will score between a 65 and an 80. All right, well here's 65, here's 80. These are just estimates. So I want all the data between these blue lines. That's what I'm calculating here. Well, here's how the zTable works. It always gives you the data below. So what we're going to do first is we're going to get the data up to and below this value. And then we're going to get the data, all of this, up to and below this value. And then we're going to subtract this value from this whole value to leave the remainder, the part between. So how does that work? Again, we're looking for the probability of a student getting between a 65 and an 80. Another way of phrasing this question is we're looking for the area under this curve between 65 and 80. If we write this in the form of probability, we're looking for the probability that our value is less than 80, that's all of this, minus the probability that it's less than 65, which is this remainder. We want it between 65, and we don't want any of the part here that's less than 65. So this is what we're looking for. In order to calculate this using the zTable, I have to convert the 80 and also the 65 into their equivalent z-values. The z-value for 80, I take 80, I subtract the mean, divide by the deviation. So that's 80 minus 75 divided by 5.5 is 0.91. So the z-value over here for 80 is about 0.91, and that looks right because it's between 0 and 1. That's what we expect. The z-value for 65. Take the 65, subtract the mean, divide by the deviation. That's going to give you a negative value. And that makes sense too, because here's where 65 is. It's between minus 1 and minus 2. The actual z-value for this location is minus 1.82. So now I have the z-values for both of these spots, and I can now use the altered formula for probability. Instead of writing it like this with my x values, I've converted the x's into z's. So now I'm looking for the probability that z is less than 0.91, that's here, minus the probability that z is less than negative 1.82, that's here. So it's still going to give me that same area, except instead of working with the x's from my data set, I've converted to their z-values so that I can use the zTable. Now I'm going to use the zTable to look up both of these values, and I'm going to subtract them. Here's what that looks like. When I look up the z-value for 0.91, that's over here. Here's 0.9, this is 0.90, this is 0.91. So I need this first number. I've written that over here. Now I need to use the zTable to look up negative 1.82. All right, here's negative 1.8. This is negative 1.80, negative 1.81, negative 1.82. So that's the value I want to use for negative 1.82. I want to write that over here. Now I'm going to subtract. And when I subtract, it gives me the area under the curve in between those two blue lines, or the probability that a student will score between 65 and 80, which is about 78.42%. So that's a lot of information, but it explains in detail how to use the zTable to calculate probabilities above, below, and between, how to convert any x value into its equivalent z value, and a reminder that you can do this if your data is normally distributed and if you know the mean and standard deviation of your data set. Thank you for joining me.